Alright, so here we are for Quideo 2. We're going to start Quideo 2 with the basic question, and it reads, here are Professor Moore's times in minutes to swim 2,000 yards and his pulse rate after swimming in beats per minute for 23 sessions in the pool, and they're listed right here. So part A of that question says, verify that a linear model appropriately models the data and state the equation of the linear model. So over here, I graphed out all the points. I put time on the x-axis and pulse on the y-axis. So time is the explanatory variable and pulse is the response variable. And I did the least squares regression line equation right here, and so that is just y hat equals a plus bx, where a is the y-intercept and b is the slope. So I plugged all the data into my calculator, and I ended up with y hat equals 479.934 plus negative 9.695x. So that's the least squares regression line equation. When I graphed it out, that was the line. It seems pretty accurate on that set of data. Part B asks, or says rather, the next day's time is 34.30 minutes. Predict the professor's pulse rate. So I plugged in the 34.30 into my least squares regression line equation, and it put out a pulse rate of 147.396. And then it says his actual pulse rate was 152. How accurate was our prediction? So I solved for the residual. It was 4.604. But I would say, considering how much of the data actually falls on or that close to the line, it's a pretty accurate prediction for this set of data. Question C says, suppose you were told only that the pulse rate was 52. You now want to predict the swimming time. Find the equation of the least squares regression line that is appropriate for this purpose. What is your prediction and how accurate is it? So for that, you have to switch the variables. So you have to end up making heart rate the explanatory variable, or the x variable, and the time the y variable, because you can't plug in the y values into y hat. It just doesn't work like that. So I had to switch the values, and I plugged them in separately into my calculator, and I ended up with this y hat equation, and it was y hat equals 43.097 plus negative 0.057x. So when I plugged in the pulse rate of 52, I ended up with a predicted time of 34.433, and the actual time that he swam it in was 34.30. So it gives you actually a negative 0.133 residual, and I said it was a very accurate prediction because it is so close to his actual time. And then part D says, explain clearly to someone who knows no statistics why there need to be two different regression lines for parts A and C. So I kind of just touched on that, but basically you need different regression lines because when it asks you, or when it gives you a certain variable, you can't just plug it in if that's not the variable you have it graphed. So I have it graphed in part A as time being my x variable and pulse being my y variable. But in question C, they were asking me, or they were only giving me pulse, so I could only plug that into x in the least squares regression line. So I had to switch my data in my calculator and solve for A and B there. Moving on to the advanced question. It says, to the right are data collected on the prices and capacities of hard drives. Below is the regression analysis of price versus capacity. So over here it's giving us capacity in, I guess, terabytes, and price in dollars. And then it gives us some stats over here. And it says in part A, without the use of a calculator, write the regression equation. Define the variables used in your equation. So I used, again, the y hat equals a plus bx formula, and I plugged in the intercept because that's what the a variable is the y-intercept. So 18.617 goes right here, and then plus the capacity, which was the slope. So that's listed right here. It's 103.929. So that ends up being my equation, and I said that y hat is the price and x is the capacity. So basically the equation reads the price equals 18.617 plus 103 or 103.929 times the capacity. For part B, it asks to explain the meaning of slope and y-intercept in context. So I said the y-intercept, which is 18.617, is where x, the capacity, is 0. So basically $18.61 or 62 cents is the flat fee for a hard drive, and the slope, which is 103.929, means that for every x increase, the y will go up 103.929. So for every terabyte that the capacity increases, the price will increase by $103. And then in part C, it asks us to predict the price of a 3.0 terabyte drive. So I just plugged in the 3 or the 3.0 into the x because that is the capacity variable, and I ended up with a price of $330.40. So in part D, it says Shaheen found a 3 terabyte hard drive for $300. According to the regression equation, determine why this is either a good buy or not. I said it was a good buy just because we said with our regression equation that a 3 terabyte hard drive should cost $330, and Shaheen found one for $30. So that's $30 cheaper for the same amount of storage. I think it's a good buy. Alright, so now with the with the AP question, it says windmills generate electricity by transferring energy from wind to a turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and electricity production in amperes for one particular windmill. For the windmill, measurements were taken on 25 randomly selected days, and the computer output for the regression analysis for predicting electricity produced based on wind velocity is given below. The regression model assumptions were checked and determined to be reasonable over the interval of wind speeds presented in the data, which were from 10 miles per hour to 40 miles per hour. So it gives us all the data right there. And part A says use the computer output above to determine the equation of the least squares regression line and identify all variables used in the equation. So I, again, use the y hat equals a plus bx, and it says right here the constant, so that is the y-intercept, so it's y hat equals 0.137. And then right here, that is the slope, so plus 0.240x. And so I said y hat is the electricity production in amps, and x is the velocity or wind velocity in miles per hour. Part B says how much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind velocity is 15 miles per hour, and show how you arrived at an answer. So I plugged in 15 miles per hour for x in our least squares regression line equation, and I got 3.737 amps are produced with 50 miles per hour winds. And I plugged in 25 and I got that 6.137 amps are produced with 25 miles per hour wind. And that would give a difference of 2.4 amps. So 25 mile per hour winds would produce 2.4 more amps of electricity than 50 mile per hour winds. And then part C asks what proportion of the variation in electricity production is explained by its linear relationship with wind velocity, and that's basically just asking for the r squared value. So the r squared value is 0.873, which is also 87.3%.